Okay, let's look at quadratics and function notation. So we have an example here of our function notation. This is some function with the input of x, and you'll notice that input or that variable occurs here, and this is the equation that we're going to input the value for. What they've told us, they said, is find the value of f at x when x is equal to 3. So when we write function notation, we would write our f, and instead of
I get the first one.
Okay.
The first one don't you just insert x in where the x's are?
Absolutely.
Yeah, that one's simple, but like I don't really get 2 and 3.
Okay, so what we're gonna recap this one because since they seem to have given you a trial and error method, we're gonna be building on this concept to do it. So think of that as a quick foundation. Since you already know it, I'm just gonna fly through the numbers really quick. That becomes 12, -5, 18 is 30, 25 I believe is our answer, right? So we get f at 3 equals 25. The page is we're going to employ this method. We're going to choose some x values and kind of take a bit of shots in the dark to see if we can get closer and closer to the answer. So let's jump ahead to the second question, like you said. This one, what they're trying to do is you need to find out when f at x is the value of 15. So before they gave us an x value, we're actually looking for the x value, or you'll notice they plural values. It's possible there's more than one, and in many of the times, it's more often there's 2 than there is 1, but there's also the possibility of having none. So let's take a look at this, how we might set up at a question like this. I'm going to rewrite it. F at x is equal to x squared minus 6x plus 8. A common way to do this would be to use something called a quadratic formula, but I don't think you've touched on it yet. You could also do some factoring. And factoring essentially takes you from the standard form, and that's what this is. This is the standard form of a quadratic. Instead of using y, they've used f at x. The standard form, you remember we had ax squared plus bx plus c. And what we want to do to find x values, those are known as roots. And the style that is best for roots is the factored form, which looks a little like this. Okay, this would be the factored form. And to go to factor form, we either use quadratic formula, that's nice about form, or we do some factoring. But again, we haven't done that. So what we're going to do, and one is like a trial and error method. You can solve many math equations through trial and error. The only problem with it is it can be tedious and at points almost extremely exhausting because you could be checking forever. A simple thing we might want to check. Starting at 0 is a nice one because it really thins out the field for us. So let's say we had f at 0. Very quickly we know that's 0 squared minus 6 times 0 plus 8. All those zeros eliminate each other. We get the value of 8. Okay?
Wait, if f of x is equal to 15, can't you just eliminate plus 8 by subtracting 8 from it and then just finding that?
This positive 8, you mean?
Yeah, like if f of x is equal to 15 and then you're trying to find what x is, can't you just do 15 minus 8 to get rid of the plus 8 so you don't have to use it anymore?
Well, one way we could do it, tell me if this is kind of what you're thinking, because it sounds like you've jumped a step here. Instead of writing the actual term f at x, I can replace that with the value of 15 in the equation. And then, tell me
and then just do it like that.
Yeah.
Yeah, that's what
Okay. What ends up being the difficulty here is you have two variables that have different powers. So that's where we usually employ a form of quadratic formula or factoring to get us down to 1. Because it becomes difficult to isolate when you have two different variables because you can't combine them because they're not like terms. Normally what you might do here is you'd bring 15 to the other side. So this side is equal to 0. You'll get x squared minus 6x plus 8 minus 15. Okay. And 0 is equal to x squared minus 6x minus 7. Now, in all fairness, this is not much different from this here. Essentially, if you look at it, our constant value is really the only difference. And that now, instead of solving for 15, we're looking for 0. That might be more helpful. It might not. As I look at it really quickly, 1 looked nice, but I don't think it's going to work out. And that probably would have been the next number we had tried in our trial and error method. I'm going to go back to function notation just because what's nice about it is it gives us a record of the x values we've tried when we're going through trial and error. So let's say we do f at 1, okay? we know we get 1 squared minus 6 times 1. And I'm going to go to plus 8. And again, we get 1 minus 6 plus 8. That becomes 9. That becomes 3. Not quite where it is, okay? And if we had plugged in the value of 1 here, we would have got a similar scenario. We would have got 1 minus 6 minus 7. It would have been a number that's not equal to 0. So we're kind of taking shots in the dark here. We can get we can start to use some inferencing. We kind of went from a y value of what was our first answer? I wrote it down somewhere. We went from 8. So this is important here. We've gone from 8, and if we take a look here, we started at x is 0. Okay, so on a graph, this is our 0, and our y-intercept was the value of 8. We then just went to the value of 1. Okay, so our x value is 1. The y value happened to be 3 in this case. So if we're drawing a quadratic, most likely we know that it's starting to come downwards. And when we're looking for x values, we're looking for when we cross the x-intercept. So we're probably on the right route. We're going to continue to increase the x value that we're plugging into the function. So let's try f at the value of 2. Okay?
Wait, what does this negative 6 represent again in the equation?
So negative 6 doesn't really actually give us an exact value of any coordinate within it. It has to do with a relationship in the equation, and we can go into Desmos and kind of play around with it. It allows it to move the entire U shape around like a fixed point on a graph. It's not something we usually go in depth in a grade 10 into solving. It's not a very clear thing to show. I can show you how to manipulate it on a graph, but they won't spend too much time talking about it. It's nothing in particular.
But I remember we went over this in like summer school.
Oh, okay. What I'll do is I'll bring it up in a graph in a second, and we'll show an example
what
of
do the
it.
numbers mean? Like the A, B, and C. Like, don't they mean something?
Yeah. So A usually does with the compression. So you'll have when you have a quadratic, the higher your A value or the higher the absolute value, the thinner the quadratic tends to be, and the closer it gets to 0. So when A is less than 1 but greater than 0, you end up getting a very wide compression like this. Okay, that's in the standard form. B essentially takes a value, say your y-intercept, and as you move it, it allows you to move your quadratic around this y-intercept. So you're keeping your y-intercept the same, and you're moving it around this point. It looks much better in an actual graphing calculator to do it simultaneously rather than my very poorly drawn out pictures here. What I'm going to do is I'm going to kind of continue our route here, if you don't mind. We'll kind of keep jumping. We're going to try the value of 2 to see if we can catch one of the roots, because we seem to be on the right track with the trial and error method. And then I'll show you an example of what manipulating B does to the standard form of a quadratic. Does that sound okay?
Yeah.
Yeah. Okay. So we were talking about this one here, f at x. And f at x, we'll try it at the value of 2. We can go at 2 squared minus 6, 2 plus 8. We get 4 minus 12 plus 8. And if you take a look at this, we end up... Oh, shoot. Why am I looking for zeros? I just realized that we're looking for the value of 15. So I've gone in the wrong route. What's nice about this is I found a 0. I know that one of the x-intercepts is 2. Okay? But the problem was I got a little mixed up when we switched into this equation here and we were looking for zeros. I'm actually still in the original form. I'm looking for the value of 15. So from our x values, we should have noticed that I actually need to go the other way, because 15 is even higher than 18, and that looks like the route that our quadratic's taking. So I might have wanted to actually try something like f at negative 1 squared minus 6 times negative 1 plus 8. We get 1 plus 6 plus 8. 15 it is. So there's one of our first examples. But what I do want to talk to you about, so we know at negative 1, so when x is negative 1, f at x is equal to 15. That's one of them. But quadratics tend to do this, which means somewhere out here, there's symmetry to them. Somewhere out here, there's another x value that gets to 15. I'm going to do a little cheating and jumping my way across. We moved over 1, we went down to 8. We moved over 1 more, we dropped down to 3. We went down to 2. We're probably going to hit the vertex here at the 3 value, and then it's going to start to come back up again. So we're going to get 4, 5, 6. I'm going to jump ahead and estimate at 7. Okay? We're going to see by just taking a look at a rough sketch of the graph, we're going to guess at 7 and then maybe jump up 1 down or 1 up from 7 to see if that gives us our 15. Okay? Did that logically make sense what I did with the visual of the graph to estimate what the next x value might be?
Yeah.
Yeah? Okay, so let's try it. I know we're going to a bit of here. But we get 7 squared minus 6 times 7 plus 8. Okay? That gives us 49. Minus 6 times 7 is 42. Is that right?
Yeah.
Plus 8. Not quite what we want. Negative 7 and 8 gives us...
Wait, so is there any faster way than this? Or is like
Yeah, so the other forms I talked about are quadratic formula and factoring, but you said you guys hadn't touched on them. So we're...
Can we go over that after just like
Yeah,
to see
absolutely.
If we can, like, understand it? Thank you.
Okay, so what we'll say here is... what did that give us? 7 plus 8. That gave us a value of 1. That's a weird value. So apparently this quadratic went a lot farther down and continued up. Essentially, we're on the right path. If we're going trial and error, we're just going to continue to go that way. So we'll kind of stop it here because trial and error is not an efficient way to do it. But it is a way if you ever get stuck. And I mentioned that at the beginning. It's not a super fast way about going about it.